Madam, please start.
Uh, Good morning, everyone, and a pleasant morning to all the students. Once again, welcome to the chemistry webinar. And dear children, do you know which topic you are going to listen today? So it's 17th group elements. In our previous sessions, you have learnt about 15th group, 16th group, isn't it? Mrs. Madhavi, PGT Chemistry from TSMS Kudu, Vikarabad, has taught you the 16th group elements and 15th group elements. And today, it's the time to learn about the 17th group elements. And what are these 17th group elements, children? The elements which contain 7 electrons in their valency shell are kept in the 7th group of the periodic table. According to the IUPAC nomenclature, they are called as the 17th group elements. And what are these 17th group elements? Fluorine, chlorine, bromine, and iodine. And dear children, there is a new element which is kept in this group. Do you want to know about all those things? So let's welcome Mrs. Madhavi, PGT Chemistry from TSMS Kudu. Good morning, Madhavi ma'am.
Good morning, ma'am. Good morning. Thank you.
Good morning, ma'am. So today you are going to teach up to which topic, ma'am?
Ma'am, up to chemical reactivity of 17 group elements, reactivity with the hydrogen and oxygen.
Okay, so you are going to teach about the reactivity of these 17th group elements.
Yeah, ma'am.
Okay. And dear children, here I want to mention you one thing. See, these 17th group elements are also known as halogens. See why they are called as halogens. Right from your first year, you will be hearing about this word halogens, isn't it? See, when you heard about alkyl halides, see alkyl halides, there also you have heard about the word halogens. Halus means salt. Genus means producers. So they are salt producing elements. And then there are very interesting features regarding these 17th group elements. So let's welcome Madhavi ma'am.
Thank you,
Thank
ma'am.
you, ma'am.
Thank you, ma'am. Good morning, one and all. A warm welcome to Telangana Model School webinars for intermediate to second year. So today we are going to discuss about 17 group elements in P block. So let us have a look of subtopics in 17 group elements, introduction about the 17 group elements, occurrence of these 17 group elements, and atomic properties of these 17 group elements. In atomic properties, we are going to discuss about atomic and ionic radii, electronic configuration, ionization enthalpy, and then electronegativity and electron affinity. Next, after that, we'll discuss physical properties, chemical properties of 17 group elements. So in chemical properties, we are going to discuss about reactivity towards hydrogen, oxygen, metals, and halogens, right? And after that, we'll discuss chlorine. So it's a preparation, properties, and uses, very important for your examination point of view. Next, after that, hydrogen chloride. So it's a preparation, properties, and uses, and some oxo acids of halogens, and after that interhalogen compounds. So these are the subtopics that are in a 17 group elements. So let us have a look today's session. So in today's session, we are going to cover these subtopics, children. Occurrence of these 17 group elements in atomic properties, electronic configuration, atomic and ionic radii, ionization enthalpy, electron gain enthalpy, electronegativity. So these subtopics we are going to cover in atomic properties, and after that the physical properties, and in chemical properties today we are going to discuss about oxidation states and trends in chemical reactivity, reactivity towards hydrogen, and reactivity towards oxygen. So again, we have reactivity towards metals and halogens are also there. So in the next session we are going to cover those reactivities. Okay, now let us start quickly today's topic, 17 group elements. Children, you have an idea about the periodic table, long form of periodic table, that is modern periodic table. So again, I want to revise it. Okay, so it is having S block, P block, D block, and F block. So where in the periodic table this S block is present on left hand side, and P block is present on right hand side, and D block elements are present in between S block and P block, and F block elements are present at the bottom of the periodic table. So from 10th class itself, we are learning all these things. So So our focus is on P block elements, right children? So P block consists of six groups: 13, 14, 15, 16, 17 and 18 group. Okay, 13 and 14, about 13 group and 14 group elements already have learned in first year. Next, in second year, you have 15, 16, 17, 18. Okay, already we have finished in previous sessions 15th group and 16th group. So today we are going to discuss about 17 group elements. So these are called as halogens, right children? So 17 group elements. So which elements are present in 17 group? Fluorine, chlorine, bromine, iodine, astatine and tennessine. So this is the new element are present in 17 group elements, right children? So fluorine, chlorine, bromine, iodine, these are familiar to you. So new elements like astatine is a radioactive element and tennessine is also a radioactive element. These are new to you, right? So now let us start 17 group elements. So these are called as halogens. So why these are called as halogens? So this halogen, this word is from Greek word. Okay. So what is that? Halo means salt and genus means bond, means salt producers. So sea water consists of many salts like calcium, magnesium, sodium, potassium salts of fluorine, chlorine, bromine, iodine. So that's why most of the salts are formed by these elements. So that's why these elements are called as halogens, right children? So the halogens are highly reactive non-metallic elements. So we know that children in S block alkali metals, the first group elements are very reactive because ns1 is the general electronic configuration for first group elements. If they lose one electron, they will get the noble gas configuration. That's why they are very reactive, highly reactive metals. Whereas in P block on right side we have 17 group elements. So they are having ns2 np5 configuration. If they gain one electron, they will get a noble gas configuration. So noble gas configuration is a stable configuration. So every element try to get a stable electronic configuration. That's why these halogens, so they are very reactive. They try to get one electron. So because of that, they are very reactive. So by gaining one electron, they form anions. So that's why these are all non-metals. So highly reactive non-metallic elements, right children? So first group elements are highly reactive metals, whereas the 17 group elements are highly reactive non-metals, right children? So now let us see occurrence of these 17 group elements. Fluorine is present mainly as insoluble fluorides. So let us see what are the fluorides that occur in earth crust. Fluorospar, that is calcium fluoride, and cryolite, Na3AlF6, and fluoroapatite, that is Ca3PO4 twice CaF2. So these are the fluorides that are found on earth crust. Okay, small quantities of fluorine is present in soil, river water, plants and bones and teeth of animals. Okay, teeth of animals. So this is the occurrence of fluorine children. Now coming to the chlorine, bromine and iodine. Seawater contains chlorides, bromides and iodides of sodium, potassium, magnesium and calcium. So but is mainly sodium chloride solution, 2.5% by mass. So we know that sodium chloride is a common salt. So from there we are getting this common salt, that is salt we use in at our home. So that is nothing but it is obtained from seawater. Seawater consists of 2.5% of by mass of a sodium chloride, right children? So that's why these are called as halogens, salt forming salt producers. So that's why these are called as halogens. Next, coming to the deposits of dry up seas contains these compounds. Example, sodium chloride and carnallite, that is potassium chloride, KCl, MgCl2, 6H2O. So the dried up seas contain so these salts, right children? Next, certain forms of marine life contain iodine in their system. For example, if you consider seaweeds, they consist of iodine. Chili saltpeter contains up to 0.2% of sodium iodate. Okay, so marine life consists of iodine. So for example, seaweeds and chili salt, peter. So these are the examples. So this is about the occurrence of the 17 group elements, children. Just you just remember. Next, coming to the electronic configuration, just now only we have discussed. So what is the general electronic configuration of a 17 group elements? Ns2, np5. So in s orbital, 2 electrons are present, and in p orbital, 5 electrons are present. Total in outer shell, there are 7 electrons in the outer shell. Okay, all these elements have 7 electrons in their outermost shell. Okay, so noble gases are having how many electrons in their outer shell? 8 electrons in their outer shell. But halogens are having how many? 7 electrons in their outer shell. So that's why these are highly reactive. They gain 1 electron and they get stability. Okay, so all these elements have 7 electrons in their outermost shell. That's why they are kept in 70 or 17 group, right children? Okay, so for example, fluorine, if you consider the fluorine, its atomic number is 9, chlorine 17, bromine 36, and iodine 53. Just if you add 8, 18, 18, 32, you will get the atomic number of remaining all elements. If you know the atomic number of first element, you can able to get the atomic number of remaining all elements. Already we have discussed in previous sessions, right children? So now coming to fluorine electronic configuration. So fluorine is having inner noble gas configuration, helium configuration. Along with that, 2s2 2p5. So what is the outer shell? Second shell is the outer shell. In second shell, how many electrons are present? 7 electrons are present, right children? Next, coming to chlorine. So in chlorine, no, inner neon configuration along with inner neon configuration, that is noble gas configuration. And in the outer shell, it is having 3s2 3p5 configuration. So total how many electrons? 7 electrons in their outer shell. And what is the outer shell for chlorine? Third shell is the outer shell. So that's why it belongs to third period. So fluorine belongs to second period. So by seeing outer shell, we can able to identify to which period this element is belongs to, right? So for chlorine, second shell is the outer shell. So that's why it belongs to second period. Chlorine, third shell is the outer shell. It belongs to third period, right children? Next, coming to bromine, in along with the inner noble gas configuration, that is argon configuration, extra it is having how many? 10d electrons. So 3d 10d electrons it is having. So and outer shell configuration is 4s to 4p5, right children? So what is the difference between chlorine and bromine? So along with the noble gas configuration, inner noble gas configuration, it is having in inner shell 10d extra electrons are present in bromine. Next, coming to iodine. So krypton 4d10 and 5s2 5p5. So in outer shell is the fifth shell. So that's why it belongs to fifth period. And how many electrons are present in the outer shell? 7 electrons are present in the outer shell. So that's why it belongs to 17th group. Next, coming to astatine. Astatine is a radioactive element. So in inner shell, it is having helium configuration and extra 14f electrons, so 4f14 and 5d10, 6s2 6p5, right children? So what is the difference between iodine and astatine? So extra it is having in a anti-penultimate cell 14 f electrons are present, right children? Next, coming to see here, so general electronic configuration, ns to np5. So in ns, how many electrons are present? 2 electrons are present. In np, how many electrons? 5 electrons are present. So if it gain 1 electron, it will get noble gas configuration. It is having short of only 1 electron. So when compared with the noble gases, okay, to get stability, it required only 1 electron. So total how many electrons are present in the outer shell in and these 17 group elements? 7 electrons, 2 electrons in s orbital and 5 electrons in p orbital. So total 7 electrons are present in their outer shell. Okay, if they gain 1 electron, they will get noble gas configuration. So this is about electronic configuration of 17 group elements, children. Next, coming to atomic and ionic radii. So we know that in period, if you move from left to right, then what happens? Number of electrons increases in the same shell, and as well as number of protons will also increases. So due to that, effective nuclear charge increases. So as effective nuclear charge increases, the size of the atoms goes on decreases. So in a period, if you move from left to right, size decreases. So who are present on right side of the periodic table? 17 group elements are present on right side of the periodic table. So that's why what happens, their size is small when compared with the other elements, elements in the other groups. Okay, the halogens have the smallest atomic radii in their respective periods due to maximum effective nuclear charge. Suppose if you consider second period, fluorine is having very small size, right, like that. Okay, if you consider third period, chlorine is having very small size because it is present on right hand side, okay, in the periodic table because of increase of effective nuclear charge, right children? Next, the atomic radius of fluorine, like the other elements of the second period, is extremely small. So when compared with the remaining elements of the 17 group, fluorine, chlorine, bromine, iodine, if you consider, so fluorine is having very small size because it is present at the top, because top to bottom in a group size increases because number of shells increases, as we have seen here. So second shell is the outer shell for fluorine, the third shell is the outer shell for chlorine, and fourth shell is the outer shell for bromine, and for iodine fifth shell, for astatine it's the sixth shell. So if you move from top to bottom in a group, then what happens? Number of shells increases. As the number of shells increases, then what happens? Size of the atom also increases. So fluorine is present at the top of the group. So that's why fluorine is having small size. Okay. Next, uh, atomic and ionic radii increases from fluorine to iodine due to increase in number of quantum shells. Okay, so top to bottom in a group, if you move, then what happens? The number of shells increases, because of that atomic size also increases. So fluorine is having small size when compared with the remaining elements. Okay, so this is about atomic and ionic radii. Next, you can see in this figure, children. So fluorine to astatine, if you consider, atomic size increases top to bottom. If you move, number of shells increases. As number of shells increases, atomic size also increases. As fluorine is having very small size when compared with astatine, is it not? So top to bottom, if you move, then what happens in a group? Atomic size increases because number of shells increases, right? So this is about atomic radius. Next, coming to ionization enthalpy. What is ionization enthalpy? The amount of energy that is required to remove an electron from an isolated gaseous neutral atom. Okay, so from an atom, if you want to remove an electron, so the amount of energy that is required is called as ionization enthalpy. Okay, so children, we know that from first year itself we have seen. So as the size increases, ionization enthalpy decreases. So it is inversely related to the atomic size, right? So now they have, we know that 17 group elements are having the small size. So because of that, ionization enthalpy is high. They have little tendency to lose electron, thus they have very high ionization enthalpy because they are having ns2 np5 configuration. So if they gain one electron, they will get noble gas configuration. So that's why they will not want to lose one electron. So high energy is required to remove an electron from ns2 np5 configuration. That too, these 17 group elements are having very small size. So because of that, ionization enthalpy for 17 group elements is very high because the ionization enthalpy is inversely related to atomic size. Okay, so next, due to increase in atomic size, so if you move from top to bottom, what happens? Atomic size increases. Just now only we have discussed, because number of shells goes on increasing. So if you move from top to bottom, atomic size increasing. So because of that, ionization enthalpy decreases, right children? Due to increase in atomic size, ionization enthalpy decreases down the group. Okay, so these points you have to remember in ionization enthalpy. Very simple. So the 17 group elements are having very small size. So because of that, ionization enthalpy is high. and that too they don't want to lose electron because they want to gain electron because they are having ns2 np5 electronic configuration. If they gain one electron, they will get the noble gas configuration, right children? So next one, uh, due to increase in atomic size, ionization enthalpy decreases down the group. So top to bottom, if you move, then what happens? Number of shells increases. So because of that, electron ionization enthalpy decreases. Next coming to, so you can see the values children. So this is the atomic radius top to bottom. What is happening? Fluorine to iodine atomic size is increasing because number of shells are increasing. So 64, 94, 114 and 133 picometers atomic radius of this 17 group elements. Next coming to the ionization enthalpy, as the size increases, ionization enthalpy goes on decreasing. 1680, 1256, 1142 and 10 8. So it means that the ionization enthalpy goes on decreasing as the atomic radius goes on increasing. It is inversely related. Next, so you can see this in this figure also, you can easily understand ionization enthalpy for a 17 group elements. So fluorine is having a high ionization enthalpy because it is having a small size when compared with the remaining elements. So if you move from top to bottom, atomic size increases, because of that ionization enthalpy decreases. Okay, so you can see the decrease in this figure very clearly, right? This is about ionization enthalpy children. Next coming to electron gain enthalpy. So what is the definition of electron gain enthalpy? So it is the change in enthalpy when an electron is added to a isolated neutral atom. Okay, so here you know that these 17 group elements are having ns2 np5 configuration. So if they gain one electron, then what happens? They will get noble gas configuration. So they can easily gain that electron. So because of that, electron gain enthalpy for 17 group elements is a high negative, maximum negative value they are having. Halogens have maximum negative electron gain enthalpy in the corresponding periods. Why they are having maximum negative electron gain enthalpy? Because they are having ns2 np5 configuration. If you give one electron to 17 group elements, they easily accept that electron. So because they will get noble gas configuration. Okay, so because of that, these are having electron gain enthalpy maximum negative value. Okay, so next coming to, this is due to the atoms of these elements have only one electron less than stable noble gas configuration. So they are having only one electron less when compared with the noble gas configuration. That's why if you give one electron to it, they easily accept that electron. So because of that, their electron gain enthalpy is maximum negative when compared with the remaining elements in the corresponding periods. Next, electron gain enthalpy of the elements of the group becomes less negative down the group. So because as the size increases, then what happens? Electron gain enthalpy decreases. Okay children, because the size increases, then the nuclear is very far. So if you give an electron, so then what happens? The attraction towards that electron will be less. So that's why what happens, as the size increases, electron gain enthalpy decreases. So electron gain enthalpy is also inversely related to atomic size. But here one point is very very important, even we have discussed in a 16 group also children. So one point is very very important. Just now only we have discussed that as the size increases, electron gain enthalpy decreases. But fluorine, when compared with fluorine, chlorine is having big size, so fluorine should have more electron gain enthalpy when compared with chlorine. But here it is not like that. The negative electron gain enthalpy of fluorine is less than that of chlorine. Very very important point children. Remember, the negative electron gain enthalpy of fluorine is less than that of chlorine. Actually fluorine should consist of more, when compared with chlorine, is it not? But here the electron gain enthalpy of fluorine is less than that of chlorine because of its small size. So because of its small size, if you give one electron to it, then what happens? Inter-electronic repulsion will take place. So because it is having very small size in 2p itself, in second shell itself, how many electrons are present? 7 electrons are present. If you give one more electron, then what happens? There will be inter-electronic repulsion because of its small size. Inter-electronic repulsions will take place. So because of that, it experiences does not experience much attraction towards incoming electron, right children? Whereas in case of chlorine, its size is neither too small not too big. So that's why if you give one electron to it, it easily accepts that electron. Because of that, it's having high electron gain enthalpy. You can see the values here, top to bottom size increases, so electron gain enthalpy should decrease. But in case of fluorine, fluorine is having less electron gain enthalpy when compared with chlorine. Very, very important point, children. Actually, fluorine should consist of more when compared with chlorine, because as size increases, electron gain enthalpy decreases. But here, fluorine is having a small electron gain enthalpy when compared with chlorine. This is due to very small size of fluorine. If you give one electron, then what happens? Inter-electronic repulsion will take place. So because of that, it will not attract that incoming electron. So whereas chlorine is having neither too small size, not too big size. So that's why it easily accepts that electron. Because of that, electron gain enthalpy of chlorine is more when compared with fluorine. So these are all having a negative values, negative electron gain enthalpies, children, because so ns2 np5 configuration, so they easily accept that electron. So that reaction is accepting an electron is a favorable for it. So because of that, this electron gain enthalpy is negative, high negative when compared with other elements in the corresponding periods, right? Next, electronegativity. What is electronegativity? Ability of an atom to attract the bond pair of electrons towards it in a compound is called as electronegativity. Okay, so smaller the size, more will be the electronegativity. It is also inversely related to the atomic size. Top to bottom atomic radii increases, so electronegativity decreases. So because of that, fluorine is having very high electronegativity. Okay, so they have very high electronegativity. 17 group elements are having small size when compared with the remaining elements, is it not? So because of that, 17 group elements are highly electronegative elements. The electronegativity decreases down the group because atomic size increases, electronegativity decreases. Fluorine is the most electronegative element in the periodic table. So in the periodic table, fluorine is the most electronegative because it is having small size, right? Left to right, size decreases. So on right side, we have 17 group elements. So that too, fluorine is the top element in the group. So that's why fluorine is the most electronegative element. In Pauling scale, it is having 4.0 highest value. Fluorine is the highest electronegative element in the periodic table. So 4.0 is the value for fluorine, whereas chlorine 3.0, bromine 2.0, iodine 2.5, and astatine 2.2. So top to bottom atomic size increases, electronegativity decreases. So fluorine is having high electronegativity, that is 4.0 value. Okay, so this is about electronegativity. Next, coming to the physical properties, fluorine and chlorine are gases, and bromine is a liquid, and iodine is a solid. Very important, children. Gases, liquids, and solids are also present in this group. Fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. So all halogens are colored. So they are having color. So why they are having color? Because in outer shell they are having one unpaired electron, is it not? So that the electron, it absorbs the radiation in visible region. Whenever we'll see a color, it means that the absorption of radiation is in visible region. So only we can able to see only visible region. So the absorption takes place only in a visible region. So by absorbing that radiations, these electrons, they will enter into the higher energy state. So because of that, these halogens are having color. For example, fluorine has yellow color, chlorine is greenish yellow color, and bromine is red in color, and iodine is violet color. Why these halogens are having color, children? Because they absorb the radiations in visible region. So only in visible region we can able to see the color, right children? Okay, so because of this absorption of radiation in visible region, these halogens are having color. So fluorine is yellow, chlorine is greenish yellow, bromine is red, and iodine is violet color. Okay, right? So next, their melting and boiling point steadily increases with the atomic number. So top to bottom, what happens? Atomic number increases. So as atomic number increases, then atomic mass also increases. So because of that, melting and boiling points also increases from top to bottom. So fluorine and chlorine react with water. Fluorine and chlorine both can able to react with water, but bromine, iodine are only sparingly soluble in water, but are soluble in various organic solvents such as chloroform, carbon tetrachloride, carbon disulfide, and hydrocarbons. So when they can able to soluble in organic solvents such as chloroform, carbon tetrachloride, carbon disulfide, and hydrocarbons. So they can able to dissolve in these organic solvents, and they can able to form colored solutions. Okay, children, fluorine and chlorine react with water, whereas bromine and iodine are sparingly soluble in water, but they can able to soluble in various organic solvents like chloroform, carbon tetrachloride, carbon disulfide, and hydrocarbons. Right, children? So this is about physical properties. Next, some more physical property. Let us see. Smaller the enthalpy of dissociation of fluorine compared to that of chlorine. So see here, actually what happens as top to bottom atomic size increases. As atomic size increases, then what happens? Bond length will also increases in the molecule. Is it not? Suppose if we consider chlorine to chlorine bond length, when it is having less when compared with bromine and iodine. So this bond length is, in the case of iodine, the bond length is more. Why the bond length is more? Because iodine is having bigger size. So in between, what is the bond length? The distance between two nuclei in a molecule is called as bond length. So here, yes, top to bottom atomic size increases, then what happens? Bond length in the molecule will also increases. So because of that, as bond length increases, then what happens? Bond dissociation enthalpy decreases. But here one more anomalous behavior that fluorine is showing. Fluorine is having less bond dissociation enthalpy when compared with chlorine. Actually, fluorine should consist of more because bond length is less. So bond dissociation enthalpy should be more. But fluorine is having a smaller bond dissociation enthalpy when compared with chlorine. Here also same reason, electron repulsion. So fluorine is having very small size. So because of its small size, what happens? So electron repulsion will takes place. So because of that, we can able to dissociate that bond easily. So less bond dissociation enthalpy is required to break the bond between two fluorine atoms when compared with the chlorine, right children? So whereas in case of other elements, other molecules, chlorine, bromine, and iodine, it is not like that. So the variation is as usual. As the bond length increases, bond dissociation enthalpy decreases. That's why Cl bond dissociation enthalpy is greater than Br bond dissociation enthalpy greater than iodine bond dissociation enthalpy, right children? So what is the reason that fluorine is having small enthalpy of dissociation when compared with chlorine? Because of electron repulsion. The reason for this is anomaly is the relative large electron repulsion among lone pairs in fluorine molecule, where they are much closer to each other than in case of chlorine. So fluorine is very small in size. Because of that, what happens? Electron repulsion takes place. So that's why bond dissociation enthalpy is less when compared with chlorine, right children? Next, coming to, so till now we have discussed atomic properties and physical properties. Now coming to the chemical properties. So in chemical properties, oxidation states and trends in chemical reactivity. All the halogens, they can able to exhibit -1 oxidation state. Why they can able to exhibit -1 oxidation state, children? Because they are having ns2 np5 configuration. If they gain one electron, they will get noble gas configuration. So if they gain one electron, means which charge they will get? -1 charge. Okay, so that's why all halogens, they can able to exhibit -1 oxidation state. Whereas chlorine, bromine and iodine, they can also exhibit +1, +3, +5 and +7 oxidation states also. Why this chlorine, bromine, iodine, they are exhibiting even +1, +3, +5 and +7 along with -1? Because they are having d orbital, whereas in case of fluorine it is not having d orbital, because the second shell is the outer shell. So in the second shell only s orbital and p orbital exist, so there is no d orbital. Whereas in case of chlorine, bromine, iodine, so they are having the d orbital also. That's why they can able to show +1, +3, +5 and +7 oxidation states also, along with the -1 oxidation state, right children? But fluorine, it can able to show only -1 oxidation state. It cannot show +1, +3, +5 and +7, because it is not having d orbital. Now you can see here, so this is the ground state, means ns2 np5, means 2 electrons are present in s orbital and 5 electrons are present in p orbital, right children? So that's why, so it shows that one unpaired electron is present. One unpaired electron, it represents that they can able to show -1 oxidation state and a +1 oxidation state. If it loses one electron, it can able to show +1, and if it gain one electron, it can able to show -1 oxidation state. So that's why, so this in ground state electronic configuration, by seeing ground state electronic configuration, we can say that these halogens, they can able to show -1 or +1 oxidation state. Now coming to the first excited state. First excited state, in first excited state, we can able to send the one electron from p orbital into d orbital. So this is possible only in case of chlorine, bromine and iodine. It is not possible in case of fluorine, because fluorine is not having d orbital, right children? Okay, so in first excited state, one electron we have sent into the d orbital. Now how many unpaired electrons are there? Three unpaired electrons. So three unpaired electrons means +3 oxidation state. Next, coming to second excited state. In second excited state also, what we'll do, we'll send one electron from p orbital into d orbital. So then how many unpaired electrons are there? 1, 2, 3, 4, 5. So total 5 electrons are there. So 5 unpaired electrons are there. So they account for +5 oxidation state. Now coming to the third excited state. In third excited state also, we'll send one electron from s orbital to d orbital. Now see here, how many unpaired electrons we have? Total 7 unpaired electrons we have. So that's why 7 unpaired electrons account for +7 oxidation state. One unpaired electron account for -1 and +1 oxidation state, and 3 unpaired electron accounts for +3 oxidation state, and 5 unpaired electron account for +5 oxidation state, and 7 unpaired electrons account for +7 oxidation state. That's why these halogens like chlorine, bromine and iodine, they can also show +1, +3, +5 and +7 oxidation states, along with the -1 oxidation state. So this is about oxidation states of 17 group elements. Now coming to the anomalous behavior of fluorine. Anomalous behavior, we know that children, second period element shows anomalous behavior. Why they show anomalous behavior? So they are having very small size and high electronegativity and the absence of d orbital. So because of that, second period elements shows anomalous behavior. So in a 17 group, fluorine belongs to second period, is it not? Because the outer shell is second shell, so that's why fluorine belongs to second period. So that's why fluorine shows some anomalous behavior when compared with the remaining elements of the same group, right? So what are the anomalous behavior of fluorine? Let us see. Ionization enthalpy, electronegativity, and electrode potentials are all high for fluorine than expected from the trends seen by other halogens. When compared with other elements of a 17 group, fluorine is having higher values than expected. Okay, so what are the higher values that it is having? Ionization enthalpy, already we have seen, because it is having very small size, so because of that it is having high ionization enthalpy and high electronegativity, because its ability to attract the bond pair of electrons is very high. In Pauling scale its value is 4.0, just now only we have discussed. And electrode potential is also very high when compared with the remaining elements of the 17 group, right? Ionic and covalent radii, melting points and boiling points, enthalpy of bond dissociation and electron gain enthalpy are quite lower than expected. So ionic and covalent radii is also very small, because left to right size decreases. So in the outer shell, total how many electrons it is having? 7 electrons it is having. So more the nuclear charge, so effective nuclear charge is more, so because of that it is having very small covalent radii and ionic radii. And melting and boiling points also very less, and bond dissociation enthalpy is also less. Just now only we have discussed what is that, because there is a electron electron interelectronic repulsion will take place. Because of that bond dissociation enthalpy is less for fluorine, and electron gain enthalpy is quite lower. So electron gain enthalpy is also quite low, because it's a very small size. If you give one electron, then what happens? Interelectronic repulsion will take place, so that's why it will not easily accept that electron. So because of that electron gain enthalpy is quite low when compared with chlorine, right children? So these things already we have discussed. Next, the anomalous behavior of fluorine is due to its small size and highest electronegativity and low, yeah, fluorine bond dissociation enthalpy. Just now only we have discussed why it is having low bond dissociation enthalpy, because there is a interelectronic repulsion. So because of interelectronic repulsion, so the bond dissociation enthalpy is very less, and this is having high electronegativity, because it is having very small in size. So its ability to attract the bond pair of electrons is very high. So that's why highest electronegativity it is having. And non-availability of d orbitals, because second shell is the outer shell. So in second shell only s orbital and p orbitals are available, so d orbital is not available, is it not? So d orbital starts from third shell. So because of that fluorine is not having d orbital, that's why it is showing only -1 oxidation state. It is not showing +1, +3, +5 and +7. Just now only we have discussed, children, right? So these are the anomalous behavior of fluorine. Most of the reactions of fluorine are exothermic. Why these are exothermic? Because it is very small and it forms very strong bonds with other elements. So small, because of its small in size and high electronegativity, what happens? It can able to form strong bonds. If it forms strong bonds, then what happens? Energy decreases. So that is an exothermic reaction. So most of the reactions of fluorine are exothermic, because if it's small size and high electronegativity, it can able to form strong bonds with other elements. So it forms only one oxo acid, while other halogens form a number of oxo acids. So fluorine can able to form only one oxo acid. Why fluorine can form only one oxo acid? Because it is not having d orbital. It cannot extend its covalency. So that because of that, it cannot form more number of oxo acids. Whereas in case of other elements like chlorine, bromine, iodine, they can able to form a number of oxo acids. So they are having d orbital, whereas the fluorine is not having d orbital. Is that clear, children? What are the anomalous behavior that fluorine is showing? Why it is showing? First of all, because it is having a small size and highest electronegativity, and it is not having a d orbital. And if fluorine bond dissociation enthalpy is very low, so because of that it is showing anomalous behavior. So what are the anomalous behaviors that the fluorine is showing? It is forming only one oxo acid, and whereas other elements, they are forming, other elements of same group are forming a number of oxo acids. Next, its reactions are exothermic, whereas reactions of other are not exothermic. Okay, and it is having a low bond dissociation enthalpy. Ionic and covalent radii are also small, less, and melting and boiling points are also very less when compared with remaining elements. And ionization enthalpy, electronegativity are high for fluorine when compared with other elements of the same group, right children? So these are the anomalous behavior of fluorine. Next, coming to uh, hydrogen fluoride is a liquid due to strong hydrogen bonding. So we know that another anomalous behavior that fluorine is showing, fluorine hydrogen fluoride, that is HF. If you consider HF is a liquid, boiling point 293 Kelvin, due to strong hydrogen bonding. So HF is a liquid, whereas HCl is a gas. So hydrogen fluoride, why it is a liquid? Because there is a intermolecular hydrogen bond, that is in between hydrogen fluoride and hydrogen fluoride molecules. There will be intermolecular hydrogen bonding. Why intermolecular hydrogen bonding is existing? Because fluorine is highly electronegative. So highly electronegative elements, in between highly electronegative elements of the molecule and hydrogen, there will be a strong intermolecular hydrogen bonding. So already we have discussed in um, previous sessions, and as well as you have studied in the first year children. So HF is having intermolecular hydrogen bonding. So because of that, it exists as a liquid and its boiling point is 293 Kelvin, whereas HCl, hydrogen chloride, is a gas. Okay, so though it is having high molecular mass when compared with the hydrogen fluoride, HCl is having more molecular mass, is it not? But it exists as a gas, right? So because in hydrogen fluoride there is a strong hydrogen bonding, intermolecular hydrogen bonding exists between the molecules of hydrogen fluoride, because fluorine is a highly electronegative element. Hydrogen bond is formed in HF due to small size and high electronegativity of fluorine. Other hydrogen halides which have bigger size and less electronegativity are gases. HCl is a gas. Okay, right? So though HCl is having more molecular mass, but it exists as a gas, whereas HF is a liquid because it is having intermolecular hydrogen bonding. Why it is having a hydrogen bonding? Because fluorine is having small size and high electronegativity. Next, so next coming to reactivity towards hydrogen. So these are 17 group elements. They combine with the hydrogen and they form hydrogen halides. What they form? Hydrogen halides. They react with the hydrogen to give hydrogen halides. But the affinity for hydrogen decreases from fluorine to iodine. So it means fluorine can able to form easily hydrogen halide, that is a hydrogen fluoride can easily form. Okay, when compared with HI, hydrogen iodide, when compared with hydrogen iodide, hydrogen fluoride can easily form, because it is the affinity towards hydrogen, it decreases from fluorine to iodine. Hydrogen halides dissolves in water to form hydrohalic acids. For example, HCl, hydrogen chloride. When hydrogen chloride, when it is dissolved in water, we'll get a hydrochloric acid, HCl. So hydrogen chloride and hydrochloric acid both are having formula same, HCl only. So hydrogen chloride is a gas, and the hydrogen chloride, when it is dissolved in water, it is called as hydrochloric acid. Similarly, HF, when it is dissolved in water, it is called as hydrofluoric acid, right children? And when HBr, when it is dissolved in water, it is called as hydroboric acid. Okay, bromic acid, hydrobromic acid. Next, when compared with the HA, when it is dissolved in water, it is called as hydroiodic acid, right children? Okay, hydrochloric acid, very familiar. Okay, Next, the acidic strength of these acids varies in the order. HF is less than, HCl is less than, HBr is less than HAE. So HAE is more acidic when compared with HF. Why? What's the reason? Because yes, top to bottom, what happens? Atomic size increases. So in case of HF and HI is having more bond and length. So more the bond length, so then what will be bond dissociation enthalpy will be less. So that's why HA can easily give H plus ions when compared with HF, HCl and HBr. So the substance which gives easily H plus ion is called as more acidic in nature. So that's why HA is more acidic when compared with HF, HCl and HBr. So what is the reason, children? Because as top to bottom, if you move, then what happens in a group? The atomic size increases. So here in case of HI, the bond length is more. So as the bond length is more, bond dissociation enthalpy will be less. So because of less bond dissociation enthalpy, it can easily give H plus ions. So as uh, the substance which gives H plus ions easily is called as more acidic in nature. So that's why HI is more acidic when compared with HF, HCl and HBr. Okay. The stability of these halides decreases down the group due to decrease in bond dissociation enthalpy in the order. So same case, children, here also the stability of these halides decreases. Same reason here also. What is that? Because top to bottom atomic size increases, so bond length increases. As bond length increases between these hydrogen halides, then what happens? Bond length, bond dissociation enthalpy decreases. As bond dissociation enthalpy decreases, then stability also decreases. So HF is more stable when compared with HCl, HBr and HA. HA is less stable among the hydrates of these halogens, right, children? So this is about the reactivity of 17 group elements with halogens. 17 group elements with hydrogen, right? Now you can see here melting points, boiling points, bond length, and the bond dissociation enthalpy of these hydrogen halides. So here, children, melting point. See comparison here. So top to bottom, molecular mass of these hydrogen halides increases. So then what happens? Molecular mass increases, then melting point should also increase. So here the increase is, you can see 159, 185, 122 increase is okay. But here when compared with the HF and HCl, this increase is not proper, is it not? Because HF should consist of less when compared with HCl. Melting point of HF should be less because molecular mass of HF is less when compared with HCl, but HF is having more melting and boiling point also. Why it is having more? Because there is an intermolecular hydrogen bond between the molecules of HF, right? Because fluorine is more electronegative, because of that melting and boiling points of HF is more when compared with HCl. Actually HF should consist of less when compared with HCl because molecular mass of HF is less when compared with HCl. But here why it is having more? Because of the hydrogen bonds between the molecules, right? HF. So fluorine is more electronegative, because of that melting and boiling points are more when compared with remaining HCl. Okay. Next, bond length. So bond length, as the yeah, if you move from top to bottom, atomic size increases, so bond length also increases. So that's why bond length 91.7 HF is having, and 127.4 for HCl, and 1.4 for HBr, and 160 for HA. So it means that what happens here? So bond length from top to bottom increases. As bond length increases, then what happens? Bond dissociation enthalpy decreases. So see here, 574, 432 and 363, 295. So bond dissociation enthalpies decreases. As bond length increases, bond dissociation enthalpy decreases. Next, this is pKa. pKa shows the acidic character. So acidic character top to bottom increases. So HI is more acidic when compared with F, right children? So because the bond dissociation enthalpy is less, so it can easily give H plus ions. So because of that, HI is more acidic and less stable. Okay, next one is reactivity towards oxygen. So halogens form many oxides with oxygen, but most of them are unstable. Okay, so fluorine forms only two oxides, so OF2 and O2F2. Only OF2 is thermally stable at 298 Kelvin. Okay, fluorine forms only two oxides. What are those two oxides? OF2 and O2F2. Out of OF2 and O2F2, OF2 is thermally stable at 298 Kelvin. So chlorine, bromine and iodine form oxides in which oxidation states of these halogens range from +1 to +7. Already we have seen children in oxidation state of the 17 group elements, chlorine, bromine and iodine. They can also show along with -1 oxidation state +1 to +1, +3, plus 5, +7 also, because they are having a d orbital, whereas the fluorine it is not having d orbital. That's why it cannot form more number of oxides, whereas in case of chlorine, bromine and iodine, they can able to form number of oxides in which the oxidation states range from +1 to +7. We can see here. So chlorine oxides, Cl2O, ClO2, Cl2O6 and Cl2O7 are highly reactive oxidizing agents and tend to explode. These are oxidizing agents, so that's why they are highly explode. Okay, next ClO2 is used as a bleaching agent because these are oxidizing agents, so that's why ClO2 is used as a bleaching agent for paper pulp and textile and in water treatment, because these oxides of chlorine are very reactive and they are oxidizing agents. Because of that bleaching purpose, this ClO2 is used in paper pulp industry and textile industry and in water treatment. So it means the purification of water also. This as a bleaching agent, ClO2 is used. Okay, next the bromine oxides, Br2O, BrO2, BrO3. Okay, so these are least stable, so these are also oxidizing agents, powerful oxidizing agents. Even iodine oxides, I2O4, I2O4 and I2O5 and I2O7 are insoluble solids and decomposes on heating, and I2O5 is a very good oxidizing agent similar to that of ClO2 and oxides of bromine. I2O5 is also a good oxidizing agent and it is used in the estimation of carbon monoxide. So estimation of carbon monoxide, I2O5, that is iodine pentoxide, is used as an oxidizing agent. Okay, so this is about the oxides of fluorine, chlorine, bromine and iodine. So these are the topics that we have covered till now, children. Okay, so now let us see what we have discussed till now. Occurrence we have seen in atomic occurrence of 17 group elements and atomic properties. In that, electronic configuration most important. What is the general electronic configuration of these 17 group elements? ns2 np5. So in outer shell, how many electrons are present? 7 electrons are present in their outer shell. Only 1 electron shortage when compared with the noble gas configuration. That's why these are highly reactive non-metals. They gain 1 electron easily. So that's why these are highly reactive elements. Next, after that, atomic and ionic radii we have discussed. So these are present on right side of the periodic table. So left to right size decreases because of increase of nuclear charge. So because of that 17 group elements are having very small size, and top to bottom atomic size increases because number of shells goes on increasing. So because of that fluorine is having very small size. After that, ionization enthalpy we have seen. So ionization enthalpy for these elements is very high because they are having very small size. So ionization enthalpy is inversely related to atomic size, right children? Next, electron gain enthalpy, very important. So they want 1 electron to get noble gas configuration. If you give 1 electron to them, then what happens? They easily accept. So because of that, electron gain enthalpy for 17 group elements is a high negative value. So but here fluorine should have more electron gain enthalpy when compared with chlorine, but it is not like that. Chlorine is having more electron gain enthalpy when compared with fluorine. because fluorine size is very small, interelectronic repulsion will take place, so it will not easily accept the electron. Okay, so that's why it cannot hold the electron because of the interelectronic repulsion. So because of that, fluorine is having less electron gain enthalpy when compared with the chlorine. Next, electronegativity, fluorine is the highest electronegative element, 4.0 in the Pauling scale. So top to bottom electronegativity decreases as the size increases. So physical properties we have seen. So next, after that, the chemical properties in that oxidation states we have seen. So what is the common oxidation state that's shown by 17 group elements? -1. So except fluorine, remaining elements they can able to show +1, +3, +5 and +7 oxidation states also. Next, reactivity towards hydrogen, so they can able to form hydrogen halides. So hydrogen halides HF, HCl, HBr and HA. So the stability decreases as the bond length increases, bond dissociation enthalpy decreases. Because of that, stability decreases and acidic character also decreases from HF to HI. Next, reactivity towards oxygen, they can able to form many oxides out of fluorine only can form two oxides. These oxides of chlorine, bromine and iodine are oxidizing agents, so as a bleaching agents. They can be used in paper pulp industry and textile industry, right children? So these things we have discussed in this session. I hope you have understood well. Thank you so much, ma'am. Thank you.
Thank you, Madhavi ma'am. Hello, children. So I hope you have understood the 17th group elements, isn't it? See, ma'am has very clearly explained you regarding the 17th group elements, that is the halogens family. So fluorine, chlorine, bromine, iodine, astatine, and the new element. See, please go through this session and write down the notes, children. I hope everyone is writing down the notes and going through the lessons which we already taught you. Why? Because all these chapters are very, very important for you, children. See, your exams are nearing by, isn't it? See, almost all we are at the end of this year, and hope you will have your exams in the month of March. And this year, you are going to write your qualifying examination also, whether it may be JEE mains or the NEET examination, isn't it? See, along with your qualifying examination, you are going to write the competitive examinations. So you should be very cautious and very careful and very attentive, isn't it, children? So please go through our sessions and watch the YouTube channel. And we thank each and everyone for giving us this wonderful opportunity. Thank you, Madhvi ma'am.
Ma'am, thank you so much.
Thank you.